pleasure to welcome our honorable guest, Professor Ravi Sinha, who will be our speaker and presenter. And Elif Ayhan will be our discussant. Elif is a senior disaster risk management specialist in South Asia region. And my name is Jolanta Crespin-Watson. I am a lead disaster risk management specialist also in the South Asia region. Let me start with a short introduction of Professor Sinha, former dean and currently professor at the Indian Institute of Technology in Mumbai. He's a civil and structural engineer, and his research has been focused on earthquake engineering and disaster risk reduction. Professor Sinha has many accolades and roles in this domain, and let me mention some of them here. Since 2015, Professor Sinha has been a member of the Maharashtra State Disaster Management Authority and is chairing a appraisal committee for the Maharashtra State Disaster Risk Mitigation Fund, recently established. Professor Sinha has an extensive experience on urban resilience as well, had a leading role in development of the Mumbai Disaster Risk Management Master Plan, and he chairs the Structural Safety Committee of Bureau of Indian Standards, and is a member of committees responsible for national standards of earthquake safety and tall buildings. And moreover, he's a member of Bridges and Structure Standards Committees of Indian Roads Congress, and chairs a national panel of experts of the Ministry of Roads and Transport and Highways in the government of India. He heads a delegation of ISO technical committee responsible for international standards on designs and structures, and represents India at ISO subcommittees and working groups on resilient infrastructure. So with that, and without further ado, I will give the floor to Professor Sinha before inviting later Elif to share her reflections, and we will have some time for questions from those connected here. Professor Sinha, are you ready for your presentation to share it?
Yes,
Thank you.
Thank you, Yolanta. And first of all, I would like to thank all of you for being here. For many of you, this is not the normal working hours, so I'm really grateful that you are here. And I'm very delighted with this opportunity to share some of our perspectives regarding resilient infrastructure, particularly critical infrastructure. So let me share my presentation. I hope the presentation is visible in the slide mode. Thank you.
Yes.
Thank you. So the topic I'm going to talk about is not taking for granted that we know how to deliver resilient infrastructure. And in fact, I would like to explore the fact that is it even achievable to deliver resilient infrastructure in an engineering sense? First of all, this work has drawn upon the work done by several of my past students. Some of them I have listed over here. Mohammad Rafiq Zoo, who's currently a PhD student, Prakash Singh Badal and Chaitanya Krishna, who were recent PhD students. Pavan Kumar did masters with me. Mahendra Meena and Rohan Shinde and several other students. So they have all contributed to parts of Insight, which together form today's talk. And also, many of the photographs I'm going to include in the presentation have been downloaded from the web, and I acknowledge that. So first of all, when we talk about resilient infrastructure in particular and DRR in general, we need to take cognizance of where we stand today. And the situation is actually quite sobering. In spite of the tremendous gains in the domain of DRR in the last 30 years, the fact remains that the decadal number of casualties due to disasters is steadily increasing decade after decade. It would have been a lot higher if the measures taken in the last few decades did not happen. But the fact remains that forget about controlling the casualties. We are not even able to limit the casualties to the level of the previous decade. And the economic losses, when we look at them, they are not just increasing, they are very rapidly increasing. And also, it appears based on the situation that the gains due to DRR efforts in the last few decades are plateauing. And what it implies is that we need DRR 2.0. DRR needs to be rebooted. It cannot be doing more of what we have been doing. We have to, of course, do that, but we also have to look at what else we have to do, which are fundamentally different. And resilience is an important concept coming from that perspective. So, before we talk about resilience, we have to talk about what do we mean by disaster risks. We seem, the DRR community in particular, seems to take into account that we understand the risks. What are important are the measures to mitigate the risk or control the consequences. But risk seems to be understood. But the facts are something else. So those of us who work in this field on a more formal level, we categorize risk into four types. We call them the known knowns, the known unknowns, the unknown knowns, and the unknown unknowns. And quite clearly, we need to recognize the fact that the risks are not all known. So dwelling deeper into this, the known knowns are the ones where the cause as well as the impact are known. And this is mainly from past experience. For example, flood disaster risks in areas which are prone to frequent flooding. Then the known unknowns, they are the ones where the causes are known, but the impacts are not forecastable. And good examples are the impacts of climate change. So the causes are known, but we don't yet understand all the dimensions of the impact with respect to disaster risks. Then the unknown knowns are the ones where the causes are not known, but the impacts can be predicted. And a good example would be earthquake disaster risk. So we broadly know where the earthquakes are likely to occur, but nothing more than that in a quantifiable way. But the impacts uh, can be predicted at least by experts, which can be used as the basis for DRR plans. And lastly, the unknown unknowns, where the causes are not known and the impacts are not known. So, for example, this would include the risk of a large heavenly body colliding with the Earth in terms of the disaster. So, when we talk about risk management strategy, then they have to be such that they are applicable to all categories of risk. So this is the big change from the prevalent mindset amongst many that risk management strategies are limited only to the known knowns. And somehow it is expected to automatically get extrapolated to the other categories of risk. And also keeping in mind the priorities, the focus should be obviously on saving lives as the topmost priority, and a nearly equal priority of managing economic losses and rapidly restoring to the normal or the pre-disaster situation. So these are the primary focus of DRR strategies. And fortunately for all of us, the global frameworks have correctly identified the principal approaches which are based on this focus. So the global frameworks often do not stay in so many words, but this is what the focus is. And in this context, the continuing functioning of critical infrastructure is essential. And what it implies is that resilience is essential in order to meet the requirements of these three focus areas. So there is no doubt that resilience, particularly infrastructure resilience, is essential for rebooting or transitioning from the existing strategies of DRR to the DRR 2.0. Now, why is resilience essential? So, as I mentioned, it's already recognized by global frameworks. So, for example, SDGs under Goal 9, they recognize that this goal should be to build resilient infrastructure, promote sustainable industrialization, and foster innovation. And similarly, Goal 11 is to create sustainable cities and communities, which includes resilient and sustainable built environment. And if we come to the Sendai framework for disaster risk reduction, target D clearly states that we should substantially reduce damage to critical infrastructure and service disruption by 2030. And in terms of translating the targets into actions, the priorities for action number one is to understand disaster risk, which also includes understand what is the prevalent resilience and what is the target resilience we should try to achieve. And priority three is investing in disaster risk reduction and resilience. So these are very nicely and very appropriately already stated in the major global frameworks, and they highlight the importance of resilience. So now that resilience has been laid out as being important, the first question I would like to raise is what is resilience? And it turns out that literature has a huge number of definitions. So there is no global consensus on what is resilience in a quantifiable way. In a conceptual way, resilience is having a consensus, and resilience means the ability to cope better with disaster in a very conceptual term. But in a quantifiable term, there are so many different definitions, and they all seem to be different. And these definitions are based on the context from which they are coming. So, the challenge is that even within a context, resilience definition should be applicable to all categories of risk. And this is where there is still work to do. And also, resilience definition should be such that it should facilitate the Sendai framework priority for action, which is to understand disaster risk. So if, for example, if we consider earthquake risk, how do we define resilience, which would also be applicable to other risks? That becomes an important challenge in front of us. And this is where I would go into in detail in the rest of my presentation, taking the example of earthquake risk. So there is some, you can say, some demonstration of how resilience can be evaluated and what it means in terms of critical infrastructure. So let's look at seismic resilience. So I would explain it in terms of a graph that if we have a critical infrastructure which has a functionality of 100% from the time of construction till the time of the earthquake event, the functionality is 100%, and then the earthquake occurs. So this results in a sudden degradation of functionality, which is caused by two factors. First of all, there is a structural damage, which is going to reduce the functionality, and then there are non-structural damage, which are going to reduce the functionality. And I have shown some these kinds of uh, funny looking portions to show that there is uncertainty on this. We currently don't have the tools or even the engineering understanding to be able to precisely define what is the extent of structural damage and the extent of non-structural damage. But the fact is very clear that the critical infrastructure in the event of a large earthquake would have a decrease in functionality. Now, immediately after the earthquake, if it was of a critical infrastructure, the efforts would start to try to restore the facility or the infrastructure. So initially, there is some mobilization time where there is no increase in functionality because this is the decision making time, the assessment time, and mobilizing the funds and so on. So there is a time gap over here, and this time gap determines exactly how much time is required before you start the work of restoring the critical infrastructure. And this is what I'm showing you is what is the trajectory which is followed for the code compliant buildings. And then after the mobilization activities are being completed, then the recovery starts. And eventually the target is to go back to 100% of the functionality, and there is a time taken for doing it. So the recovery time is the time from the earthquake occurrence to the time when 100% of the functionality is achieved. Many times we cannot achieve 100%, so there is going to be a decrease at the end of the process, and it would be somewhere close to 100%, but not equal to 100% functionality. And also sometimes we are able to get build back better, so the functionality is even improved compared to the pre-earthquake position, so we can go above 100% also. So it is not that we always target 100% functionality restoration. It depends on the circumstances. Sometimes it would be less, sometimes it would be more. So this is the current situation of how it happens, and this time duration can be unduly long, which is one of the reasons why we have low resilience with respect to the particular infrastructure. What we want to do is to have a situation where the sum of the structural and non-structural damage, they do not decrease the functionality to the same extent, so the functionality loss is reduced. And secondly, the trajectory of recovery is much faster compared to the current situation. So a disaster resilient infrastructure would have this kind of characteristic, that it would have much lower loss of functionality compared to the current situation, and it would also have a much faster recovery process. So the characteristics is like what it translates to is that it has to focus beyond safety. Safety is only defined in terms of structural damage, but here both structural and non-structural damage should be limited, and it should be limited not looking into the safety of the building, but looking into the functioning of the infrastructure itself. So we desire to maintain the functionality at the earliest, and when we cannot do that, we want to recover rapidly. These are the key attributes of a resilient infrastructure, that the initial focus should not be code alone, which are safety specific, but beyond code in a quantifiable way, so that you can engineer it, and to maintain functionality, which is always not always possible. So in that case, recover rapidly. So, so in order to do that, we need to assess what is the difference or what is the gap between the code path and the resilient path. So this is the resilience gap which we have. And at least for critical infrastructure where quantifiable engineering has to be implemented, we need to be able to measure it, and we need to demonstrate that the actions which are being proposed to take makes us reach the desired path, so that we know what is the net outcome in the next earthquake disaster. So the question is, how do we assess this seismic resilience? So we recognize, all of us know, that modern buildings are designed following life safety based prescriptive code standards, and the conventional design approaches focus only on structural performance and immediate loss. There is a new paradigm known as performance based seismic design, and if it's a performance based seismic design, then in that case, in a very, very limited way, the performance of non structural components are considered, but that happens only in a handful of countries, and that too also very imprecisely. So functionality per se is not yet an engineering parameter in standard design standards, and there is a lack of understanding of the resilience parameters. So in fact, we in our work, we divide resilience into three baskets: reoccupancy, how quickly can we reoccupy the facility; second is functionality, how quickly can we restore the functionality; and third is the recovery performance, so what is the path which we take to recover. And all three are different ways in which they can be controlled through engineering, is what we are trying to propose. So unless we understand this, there is a limit of the improvement opportunity, and it inhibits the risk informed decision making because let's take the example of a critical hospital or tertiary hospital. So initially in the initial days and weeks after an earthquake disaster, we may just want to reoccupy it and not have it fully functional. So maybe the operation theater is still not working, but at least we can have a place for the doctors to come where the injured people will come and show themselves. So there is a partial use still possible if we have taken care of reoccupancy, even if the functionality is not fully restored. So there are these opportunities, these kind of nuanced decisions which can be taken if we understand these parameters well. So, benchmark performance of modern archetypical reinforced concrete buildings can be determined, and it is possible to assess using the performance-based seismic engineering framework what are the collapse probability, what are the likelihood of red tagging, how much, whether the building is going to have irreparable residual drift, and also parameters such as repair cost ratio compared to the initial cost of construction, occupancy time, functional recovery time, and the full recovery time. And we have done some work which I am going to show very, very quickly for IS Indian Standard Code compliant buildings. And we have considered earthquake hazards or the earthquake occurring on the buildings with varying return period from 50 years return period to 10,000 years return period, so that we get a range of understanding of what an Indian Standard Code compliant building's performance in terms of functionality is going to be for various strength of shaking. And the objective is to identify the gap between the code level performance, which is the safety based performance, and the requirements from resilience and sustainability perspective. So there's a methodology, as I mentioned, performance based seismic engineering methodology. I don't want you to understand this graph I'm showing. I just want you to know that there is a procedure which is a globally accepted procedure, and we have applied it to a building, and I'm just showing a sample frame of a building. It's a 3-story building. I'm just showing the sample frame of the building on which this procedure has been applied. And there are a number of inputs which are required. There are a number of decision variables which have to be considered. And at every step in the analysis, the uncertainties have to be considered in terms of the material properties, in terms of the strength of shaking, and also in terms of the engineering uncertainty in the modeling itself, which we have done in this particular study. So, and the reoccupancy, functionality loss, and recovery, their assessment we have drawn on the information or the prescription given in a recent Applied Technology Council report known as ATC 138.3. And for each earthquake, so there are large number of earthquakes which are considered. For each earthquake, we have considered 5,000 Monte Carlo simulations of the building to take into account the effect of variation in strength of concrete, strength of steel, and also how the nonlinear behavior after damage occurs. And now here I'm showing, so I showed you the building model earlier, and this is the final building model whose results I'm going to show. So this is the plan of the building, and this is the elevation of one of the typical frames of the building. And it's a commercial building, so fulfilling a major critical function, like for example, a telephone exchange or something. So I'm just straight away jumping into the results. And what I want to show you is that depending on how rare the earthquake is, so the x-axis is the return period, what is the probability of various consequences which we have evaluated. And what I'm showing over here is the median probability. So there is a variation along all the lines which are shown over here. So there's standard deviation or a scatter. And what I'm showing is from the bottom to top is the collapse probability, the probability of excessive residual drift so that the building is standing but it's not repairable, the probability of red tagging the building, so the building is repairable but it cannot be entered unless it is repaired, the probability of loss of reoccupancy, so we cannot quickly reoccupy, and the probability of loss of functionality, that the building is not able to meet its functional requirement. And there is a line over here of 2% in 50 years. This corresponds to what we call in the standards as maximum considered earthquake. So typically the critical facilities would be designed for this level of earthquake. And then we have 10% in 50 years, this other vertical line, which typically corresponds to the design earthquake force for the non-critical building. So what we are seeing over here is that for this critical building, there is nearly 100% probability after the earthquake that it would not be functional. And after the earthquake, we cannot simply reoccupy. That probability is also more than 80%. And this is a building which has been designed as a critical facility and meeting all the standards requirement, which means that the life safety in terms of what will happen to the occupants at the time of the earthquake, that life safety is well taken care of. But when people are able to walk out of the building or escape from the building, coming back is hampered because there is a more than 80% probability that the building cannot be reoccupied. Then there is also almost a 60% probability that in the standard evaluation methods, the building is going to be categorized as red tagged, which means that even temporary reoccupancies, let's say the daytime reoccupancy for some functions would not be permitted. And there is also a small probability that the building is going to either have excessive residual drift or would collapse altogether. And this is for a code compliant building we are talking about over here. And if you look at what it takes to repair the building so that it can be restored to full functionality, then in that case, even if the building is having a very low probability of excessive drift and collapse, the repair is always expensive. So a low probability of this kind of excessive damage does not mean a low cost of repair. So here I'm showing some of the same situations. So here I'm showing the results as in terms of the scenario expected loss, this line, scenario upper loss, and the corresponding median loss, and this is the topmost is the 90 percentile loss. So at 2% in 50 year, which is our target earthquake, we can see that anywhere from 30% to 70% of the replacement cost of the building would be required in order to carry out the repair. So these are not inexpensive damage in case we want to repair functionality. And that's one of the reasons why it is so important to reboot this whole concept of DRR from the point of view of resilience to ensure that these kinds of very heavy and very time consuming expenses can be avoided in the event of a disaster, even though the building meets the life safety requirement. And one more result I want to show you over here, which is the median recovery time under various strategies. So there is a strategy I'm showing over here, and this is a FEMA report, FEMA P58, which gives the procedures of how these calculations can be done. So if a number of steps are required for repair, if they are carried out in parallel, then in that case the recovery can be very fast, the bottom one. But quite often it is not possible to carry them in parallel, because particularly if we are having multiple floors with damage, we need to carry out the repair on one floor, make it safe, and then only go to the floor above. So series is more commonly likely. Then the series repair would have this kind of a trajectory. And if we are looking at just the reoccupancy, then we have a trajectory like this, and similarly for functional recovery and full recovery. So there are certain trajectory, and again this vertical line of 2% in 50 years is our interest line. So the recovery time is shown in days, and you can see that the recovery time would vary anywhere from nearly 100 days to even exceeding a year. And what it means is that this critical facility, which did not kill anyone who was occupying the building, would be out of action from anywhere between 100 days, about 3 months to 12 months. And this simulation has been carried out by assuming that we did not have any wastage of time in mobilization of resources and taking decisions. To this, we have to add what is the time required in order to decide that we want to carry out repair, to get the resources, and to get the engineering assessment done, so that the repair strategies can be decided. So we have put that time as 0. Even then, this is how long it takes for this example structure for the restoration of its functionality. Then there are a few other results, but I will not go into it right now because they are like a slightly higher level of results. But what I want to emphasize is that the jury is still out in terms of whether we can assess disaster resilient infrastructure. So, because we want to have disaster resilient infrastructure, that is very clear. But uh, but the tools required to assess how resilient we are currently and what are the additional steps which are required to make them more resilient, those tools are still under development around the world. And some very important steps have been taken through a few publications like FEMA P58 and ATC 138, and also several journal publications. But this is work in progress. And what I want to emphasize with specific context to the example is the Indian Standard Code confirming building have high probability of losing reoccupancy and functionality performance under the code level earthquake events, and also that these buildings will experience extended reoccupancy and functionality recovery time. So it is not that because they are life safety damage level, so they can be quickly reoccupied. And also mobilization time which is required to arrange resources for repair will have a major influence as added time for post recovery reoccupancy compared to the results which I have shown you. And the study reveals that there is a need to incorporate functionality and recovery performance objectives in the design and assessment approach. So this is not something for all structures, but we are talking about the critical infrastructure over here. So for critical infrastructure, we have to go beyond the codes and standards. And what I have described today is one of the pathways through which we can go beyond the code so that the methods are science based and not art based, which means that different engineering groups will come to the same conclusion and would be able to use the same process for developing the methodology to ensure resilience. So I would just like to conclude by acknowledging for one of my PhD students the Prime Minister Research Fellowship in India. And also I want to acknowledge that some of the analysis used a commercial software known as SP3, for which we have received the academic license free of cost. So thank you very much. I've just tried to give a perspective of how engineering-based resilience can be incorporated in the design of critical infrastructure. And this perhaps is one of the paths through which we can reboot DRR to now go beyond life safety and look at resilience as the key objective. So thank you all.
Thank you very much, Professor Sinha. Certainly lots of food for thought and important aspects of which we you discuss, with which we often grapple in our supported by the banking investments and in discussions with the government on priorities and actions on strengthening critical infrastructure against earthquakes, but also other type of hazards. So with that, let me invite Elif Ayhan as discussant to follow up and maybe share her thoughts and feedback and reflection. So Elif, floor is yours.
Thank you so much, Yolanta. Thanks, Professor Sinha. Thank you so much for your excellent presentation. You took us from presenting and discussing the concepts and posing so fundamental questions to the granularity of design and assessment, and left us with really the key question to me: how do we make it happen? How do we make it happen given this uncertainty of earthquakes? The box that you nicely put it, unknown knowns. We know it will happen. We know what it will produce. We know the impact. We just cannot define the exact timing and the location, which is, of course, key to saving lives and saving critical infrastructure as well. So in the bank, of course, our aim is to take these concepts and uncertainties, and as Yolanta mentioned, convert this into something reasonable, meaningful to our government counterparts, for them to act on under very, very solid, concrete frameworks, which could be investment operations, which could be policy actions, institutional actions, all aiming towards creating change, improving resilience of critical infrastructure, saving more lives on the ground. So indeed, it's easier said than done. But of course, we also have a couple of really flagship programs under implementation over the years, maybe over almost 20 decades, for improving seismic resilience in several regions. Of course, again, the evidence that you kindly shared with us prove nothing replaces, after action replaces building it properly and building it to the standards or the requirements that that piece of critical infrastructure may deserve. So one critical note, one main note that I take away from your presentation is we should definitely do more about avoiding new risks, knowing that even low probability of damage requires expensive and often lengthy interventions to bring it back to hopefully same functionality or to some functionality. Nothing replaces building it properly, building it to the standards, to the requirements in the first place. That's one thing. Second, this uncertainty shouldn't discourage us. There are ways, depending what you shared with us is about critical infrastructure, which obviously requires more attention or different approaches. But this shouldn't this shouldn't discourage us to tackling this problem, because depending on the type of the structure or the importance level or the occupancy level or the functions, we may bring different approaches. We may aim for different performance levels. It could be life safety for some structures, but definitely for some pieces of critical infrastructure, it should be beyond. We should aim for seamless functionality or bringing back the same or even better functionality as soon as the disaster hits. In some cases, like we see maybe for hospitals, they should even be functional at the time of the earthquake and immediately after it to serve people. Another note that I took from your presentation is, of course, when we introduce non-structural damages into this mix, that unknown portion even becomes larger. Nonetheless, when we think about critical infrastructures such as hospitals, non-structural damages also play a major role in the functionality. I also took note of your you have a long list of course, responsibilities and functions yourself as being a prominent professor in this area. But your role in preparing the Mumbai DRM master plan, a metropolitan city of gigantic scale, and also your work on working on disaster risk reduction, disaster risk management funds. That attracted my attention, and given the uncertainty and problems and your functions and how to make it happen, I would be very much interested to learn more about how this experience, conceptual questions, and the practical evidence translated into the Mumbai DRM master plan. I had the chance to have role in a similar earthquake master plan for the metropolitan city of Istanbul in Turkey. Uh, Remembering those days, that master plan was 1,300 pages, and it was a beautiful document. But then, including myself, many people involved were also questioning, what does it mean for the practitioner? What does it mean for the mayor or a decision maker in the government? What does it mean for the person on the street? What guidance that provides us? And even when you have the most practical implementable master plan to not create any further risks and reduce seismic risks, how to fund it is a different question. That unknown piece definitely prevents decision makers or the budget holders in any governments anywhere in the world to put immediate money to something that's uncertain. They have more pressing and daily needs to manage, immediate services to be provided to citizens. So how to fund all of this operation, reducing risks, not creating new risks, is also something that we would be very much interested to learn from your experience. Thank you.
Thank you very much, Elif. There were a lot of good reflections, but also questions to Professor Singha. So, Professor Singha, what would you like to take on those all quite difficult in practical terms often issues that Elif mentioned?
Yeah, so thank you very much. Interestingly, we learned many lessons from the Istanbul Risk Management Master Plan when we took our workup. And one of the important lessons which we took is there's a difference between a master plan at a conceptual level and master plan at implementable level. So, in terms of our procedure, we took several additional steps in developing the Mumbai Risk Management Master Plan. And one of the things we did was that we carried out a very extensive study of the legal and administrative provisions behind all the government agencies which are involved in actions after a disaster. And we sat with them and we helped them develop their SOP based on the master plan. So master plan was not left at the master plan level, but it was translated into administrative orders within those organizations of what they would do differently now after the master plan has been prepared compared to what they were doing earlier. And this was particularly important as we realized because most of the complicated action had to be taken in coordination with many agencies. And coordination is something in which they have very poor work experience. So, unless there are SOPs in terms of administrative orders given to the officers, their ability to coordinate and to accept orders from others from another organization, that is not very much. So this was the important lesson which we took from a similar effort in Istanbul and Metro Manila to ensure that we are able to give a more implementable master plan. And in the case of Mumbai, now it has been more than 10 years since the master plan has been implemented. And we didn't really, till 2020, we didn't really have a large scale disaster to see whether it works or not. But the pandemic showed that even though pandemic was not planned, what I have mentioned to you earlier in the presentation regarding the ability to make plan for one and use it for other disasters. So in the case of Mumbai, we saw that that was very effectively and very seamlessly done during the pandemic, because the same structures, the same financial mechanisms, the same administrative mechanisms could be used. The second issue which I would like to address is the mitigation fund, which has been recently over the since the last 2 years, which has become available in India. So at least for our country, this is a very pathwaking step, that now there are funds available which can only be used for mitigation projects. And in the case of the Indian situation, the funds have a 75% contribution from the national government, from the federal funds, and 25% contribution from the state funds. And the funds are quite sizable right now. So for my state, Maharashtra, this year, the funds which are available under this category are equivalent to about 400 million US dollars. So it's quite a sizable sum, when in the past there were almost no mitigation activities, that now you can start taking mitigation activities. And one of the decisions which we have taken right now is that the only projects which would be considered are the projects which are recommended by the local disaster management authorities. So they have to be responsible that this is a mainstream activity and they would be able to use it. And only such projects we are accepting. We are going to expand the scope of the fund in due course. Uh, and also based on the experience so far over the last few months since the fund became operational, we see that there's a very important role for the bank to come and help develop the framework under which the fund should be used. So when I come and meet you, I will discuss some of my ideas so that you can also see whether this would be feasible and workable for the bank. But we are very excited about the fact that there is a dedicated fund which can be used for mitigation activities, compared to earlier when mitigation and development were sort of mixed together, that only the developmental projects could be used for mitigation. So thank you.
Thank you very much. No, I think this is great development on the fund side. We had discussions of this type of mechanism in some other countries. I remember in the Philippines as well, where there was portion of the fund, but very small originally, comparing to the funds that were reserved for post-disaster response. But really, we are very glad to hear about this new fund in Maharashtra, and we'll continue these discussions a little later in detail. With that, I would like to give opportunity to our participants and audience for questions or any comments. I see first Fernando. Fernando, please go ahead.
Thank you.
And please raise hand with the others who would like to ask question or comment. Please use the hand in the Teams. Thank you.
Thank you, Yolanda. Thank you, Professor Ravi, for this interesting presentation. I am very glad to see the highlight of including functionality as part of the resilience concept on top of safety considerations. I think we are working the same line in our work related to school infrastructure. But let me share with you 3 challenges that we find in our work with client countries on trying to apply this approach on for the recovery or for the mitigation of seismic risk in school infrastructure. One is regulation. general building codes do not include the performance-based approach for new buildings, and even is the gap is even bigger regarding existing building retrofitting works. So there is a gap of regulation, so that most of these tools cannot be used or cannot be applied for actual projects. The second challenge is capacity, local capacity in the engineering community. The performance-based design approach brings many advantages in terms of efficiency of the design, in terms of understanding the performance of the building, in terms of understanding the recovery and the functionality of the building. However, there are limited capacity out there in terms of use these modern structural engineering tools. And the last challenge I want to mention is how to use this approach for large number of infrastructure, because the performance-based design it's quite useful and is common. Is usually applied to complex buildings, for example. But when we talk about the schools, if you think a school, one school is very simple building. But if you talk about 40,000 schools, so there is a problem of scale. So I would like to mention this to you because it's part of our experience trying to push this agenda further. Thank you.
Yeah, so thank you, Fernando. This is a very important set of points which you have raised. I think the first and most important issue which we need to address is local capacity building in the engineering community and also in the contractor community to implement these more advanced designs. So we need to pay a lot of attention because this capacity building is not going to happen organically. It has to be, it can be achieved at scale only through dedicated programs intended to develop these capacities. So we seem to, even we have made that mistake in India, that we seem to assume that we take pilot projects and through the pilot projects there is the experiential learning and that can cascade into capacity building. But on many of these complicated engineering concepts, we are finding that that is not sufficient. That pilot projects should be there because we want to introduce new methods, new materials, and so on. But that cannot be a substitute to dedicated capacity building. And the second issue is related to can you apply these methods at scale? So at least the one which I presented, this is intended for critical infrastructure, and I hope that this would not require to be implemented at scale because this requires very high level of engineering expertise. But there are a small number of facilities where that requirement would need to be fulfilled. But at a much larger scale, there have to be simplified methods which can be used at scale for buildings or for infrastructure facilities where the requirements are not as complicated and where you can make some simplifying assumptions to do. So these are going to be, you can say, future developments. But right now we need to recognize that these are gaps where we are not able to address. Thank you.
Thank you very much. And I would like to ask if there are any further questions. I don't see hands, but please you can just speak if you have any questions. No, it's not at this point. So maybe from my side, it's I was very glad actually to see at your graphs the clear indication that even in the engineered structures built to the code or retrofitted to higher standards, we have to expect some time for mobilization, for recovery. You know, what we often see that when we engaged and the government starts investing in, for example, large-scale retrofitting programs and investments, particularly on retrofitting, the expectations are really high from the beneficiaries, whether we talk especially on hospitals, on schools, and other lifelines. And the expectation generally usually is that these facilities, once they are retrofitted, they are kind of earthquake proof or disaster proof, and we know it is not possible. It's just, we will always have the black swan events, and you cannot build to 100% certainty. As engineer, you understand very well. So really, we see issue of managing expectations, and this might not be the prime occupation of engineers, but also engineers probably will have to be part of managing these expectations vis-a-vis decision makers and the public as well. But also, you mentioned importance of the non-structural aspects, and this is, for example, in hospitals, not only lighting and equipment, bracing, etc., but importance of working together with other agencies such as disaster risk management agencies, to help with basically surge capacity, for example, in case of hospitals, and have these hospitals designed not only being concerned about building themselves, but also the siting, so there is a space for temporary facilities, etc. So there are many things that come in addition to engineering standards. So and one more point from me, Fernando mentioned, codes, capacities, and scale. Huge issue that we have in all countries practically we work with is compliance. It's compliance with those standards, with those building codes. So let me stop here. But yes, any reflections on how you see in India or elsewhere, to raise this awareness and managing expectations as well, and how to work together between the engineering communities and all other important actors to ensure this the resilience, but not disaster proofing of the critical infrastructure. Thank you.
No, so thank you for this insight, actually, and I agree with all the points you have mentioned. And in the case of India, also compliance is a very big challenge, and sometimes we feel that it's almost like a cultural challenge and not just something very simple to overcome. And so we are also struggling with various measures through which compliance can be improved. It cannot just be a top-down order kind of thing, because we may have all kinds of orders in place, but if people don't want to follow it, then it's not going to be followed. So it has to recognize the fact that the people should be willing to follow. So that will come through their knowledge of the importance of this, as well as a better understanding of their role in terms of life safety and continuing functionality. So it's a lot of sensitization which has to go in addition to the new provisions in law. And in India also, we are trying a lot of different things. So the bank team from India is taking lead in that, and some really good measures they have taken, and we are looking forward to seeing how effective they turn out to be.
Thank you very much, Professor Sinha. I don't see see any hands raised, and we reached already. We got a little bit over, but we started 4 minutes later too. So we are right at the mark of 1 hour. Obviously, we just started scratching the surface. There is so much to follow on, but these are really good reflections, and I want to thank you for your presentation, and thank Elif for really good points that she raised. And to those who connected, as I mentioned, we will distribute the copy of presentations. Thank you, Professor Sinha, for agreeing to that, and the recording. And I will see you a little later today. Yes. Thank you very much.
So thank you all for this opportunity, and I look forward to further interactions so that we can continue the dialogue.
Thank you.
Thank you. Bye-bye.
Bye.
Bye.